All right. Okay. So just the overview, we're going to give a quick introduction to the Energy Club and then overview of Energy Week, which is this week. Then we'll go into the Spark Talk research and presentations and questions. So each person will present and then we'll give a few minutes for questions and then we'll move to the next presenter. Then we'll have voting, which I'll provide the form when that comes. And then we'll have a chance to either meet the presenters on, we'll try to do our best since it's hybrid, but meet the presenters and we're having more pizza. So I want to go over Student Energy Club at NC State, and we really encourage you to get involved. Some of the activities we help with is Energy Week, which includes this week. We do webinars and seminars, panel discussions, outreach, and networking, and some photos here from some of our past events. And our mission is creating pathways to foster active interdisciplinary collaborations between departments at NCSU. Together, we provide a platform for energy experts of today to educate the NC State community on the critical challenges the energy system faces today and the emerging technologies that are being used to mitigate them. It was formed in 2018 as the first campus-wide student energy club on campus. And we have now, I guess by members, as I go off of who's on our email list, we have over 200 people on our email list. And this includes a variety of faculty, staff, and students. We also have people outside the NCSU community attend, and we're really, I think, probably one of the more diverse clubs. Like, this is just a sample of some of the departments, but I didn't even add some of the newest ones. Like, we have some business majors who are active with us, industrial engineering. So we really focus on diverse membership for a variety of perspectives. And so we have a few leadership members here. I'm the co-president, the other co-president couldn't make it today. I don't know if you guys want to introduce yourself in the back.
Hi, I'm Jada. I'm the chair of the Revenue Affairs and Outreach.
I'm Colin. I'm the treasurer.
So if you want to get involved, just let us know. We really welcome new members either on our email list or just as a leadership team. So our current initiatives include education on important energy related issues. So I mentioned webinar and seminar, panel discussions, workshops, energy research, the Student Energy Week, and mentorship program. So we've done a number of educational workshops, including Electricity 101, the US Grid Explained, and communicating your science with the public. And we actually have another 101 workshop tomorrow as part of Energy Week, Nuclear Energy 101, which I'll talk more about. We did a series of a lot of webinars especially during COVID. So we'd had one on nuclear safety, sustainability, and risks, as well as natural gas and the Biden climate agenda. And I have some examples of some of the other webinars we did, and we're transitioning more to in-person now. And we had a talk on energy justice with Dr. Destine Knock. And we did an energy spotlight series where we did interviews with leaders in energy at NC State University. So if you want to go, you can it's pretty easy, just search for NCSU Student Energy Club and we should be the first hit, or you can let me know and we can add you to the email list or let you know about other leadership opportunities. So let me briefly talk about NCSU's Energy Week. This is an annual event that happens for the whole week and it's just starting. We had the first event on Friday. This is the second event and then we have events the whole rest of the week. So I'll just scroll through quickly. Tomorrow we have an energy entrepreneurship panel. And the same thing, if you search for NCSU Energy Week, all of these, you should see the whole schedule with the events. We have Nuclear Energy 101 on Wednesday. Sorry, I said tomorrow, Wednesday. We have a campus utility power tour, plant tour, which if you haven't been on, is really cool to see, so I'd recommend. We have the electric vehicle showcase. We can see electric vehicles, and I think they're going to have food trucks at that event. We're going to have the future of clean transportation in North Carolina. We're going to have a social hour, NC State University energy preview, and then a food science building tour. So a lot of fun events, especially hands-on. So I really recommend you to check these out, and everything's free. So with that, I want to give the presentation order. So we have 3 people presenting in person. I'm also presenting 2 presentations, but I will not be competing in the competition. And the last person will be presenting on Zoom. So, Rahul, are you ready?
So we have, yeah. Hi everyone, my name is Rahul Chakraborty. I'm going to present today the topic power flow optimization redesigns for renewable integrated power grids, different methods, architectures, and risk analysis we did for this work. This is part of my PhD thesis, and I want to acknowledge Dr. Anna Chakraborty for his guidance. So yeah, without further ado, I'll go jump into a brief summary of the topic. So this is only the one slide I kept. The overall concept is you can see different images of renewable plants, but at the center of it, we see the smart grid. So we are pretty familiar with the term that grid is becoming more complex, and with different integration of machine learning techniques and fast actuating resources, the grid is becoming smarter. So we are having a lot of control capabilities. With the current control architecture, we don't utilize all the resources to its full extent. Like the conventional generators, they are like locational spread-wise, they are not that accessible to have a distributed control. And when we see the wind plants and solar plants, they have pretty much two types of variations. One is utility scale, bulk energy resource, and then there are like rooftop PVs, which are spread in the distribution feeder. What we try to do in this work is we try to take the advantage of the fast acting capabilities of the renewables, try to take the advantage of their locational spread, and also address that the uncertainty which comes from renewable, how we can minimize that while utilizing them to the maximal extent. So that's the overall idea. Now, we know that US is like a big country, and unlike the European countries like Denmark or Germany or Finland, which have their country-specific solution. One is like more on solar, one is like more on wind, but US can't have a uniform solution. It will be like location-specific. Like Hawaii is 100% renewable-based system now, but if you consider the main Western or Eastern grid, they are like a mix of conventional generation, nuclear units, and renewable plants. So we need to analyze like the local solutions for US, and if there is like emergency control, how we can utilize the local resources without disturbing the entire grid. So our power flow optimization try to take advantage and solve the local power flow in a hierarchical way. And we try to address different system level objectives, like how to make the steady state performance better, how to make the transient performance with lesser settling time for different type of like load generation imbalance events. And also we came up with certain power flow algorithm which sets the renewable plants to a certain set points, which makes the stability of the system better. If there is any huge transient disturbance, the system should likely survive. Like hurricane happens or thunderstorm alerts happens in New York, and they adjust their set points in an ad hoc way right now in the current architecture. But with our methods, they will have a better control and better stability margin for their system. So it's like how the cyber physical architecture is integrated with a better power flow optimization. That's the topic of my research. Thank you. Now, if you have any questions.
Do you work on a specific area or?
Yeah, so there are like 3-4 problem statements I work on. Mostly they are related to transmission system, and power systems are like multi area power systems right now, like the western part and the eastern part, they have their own area, like New York, New England. So if you have a multi-area, one of my problem statement was like how to come up with the area specific solution. Consider like a utility, if it has its own disturbance, it will try to mitigate with its own resource before asking from help to the neighboring utility. That was one of the problems. There are many types, but the overall idea was to have a better power flow optimization.
Okay, so next up, I will present on my work on the climate and health implications of adopting modern cooking fuels. So let me first talk about the health and climate burdens of cooking fuels. So energy sources all over the world are needed for cooking and water heating, and approximately 2.8 billion people cook using solid fuels. Approximately 1 billion people lack access to safe drinking water, and 1.2 billion of household water treatment users boil water. And so all of these daily activities require solid fuels, and solid fuels emit many pollutants. So, and the PM2.5 emissions, which these pollutants emit, have health impacts. And so this results in about 2.6 million deaths annually due to household air pollution. And so they also emit what we call short-lived and long-lived climate forcers. So biomass burning is responsible for approximately 0.4 degrees Kelvin warming over 20 years. So not only are there health impacts, there's also climate impacts. So in this study, we did a global study of the LPG and electricity as modern cooking solutions. So we used historical population and fuel use trends, and we had developed from this different scenarios. So we had a business as usual scenario where we kept the same fuel use trends and projected them forward. We had a full transition to LPG and electricity scenario where the LPG use was projected forward and then electricity was making up the difference. And then we had this hypothetical 100% clean cooking scenario, which never can realistically happen, because even if you cook on electricity, when you're producing that power for electricity, that creates emissions, or if you're producing gas, that creates emissions. But we just want to see what happens if we completely turn off emissions. And we wanted to calculate the change in PM2.5 to quantify health impacts, and we used the FAIR climate model to calculate the change in global temperature. And we focused on countries with greater than 1 million solid fuel users, so 77 countries. And so we had a lot of different results, but for today, I'm just presenting our main one, which is attributing global temperature decrease to country emissions. As you can see here, some of the different countries and the decrease in global temperature impacts from the full transition scenario to LPG and electricity. And you can see like China and India as expected have some of the biggest impacts, but also there are many countries sub-Saharan Africa, such as Nigeria and Democratic Republic of the Congo and Ethiopia, where if we transition to LPG and electricity, there'd be a significant decrease in global temperature. However, this study was just a pure hypothetical modeling study, so a lot of work would need to be done to actually implement these cleaner solutions, but it shows that there's a lot of potential. So thank you. Yeah.
What was LPG?
Oh, sorry, I should have defined it. So it's liquefied petroleum gas. Yeah. Yeah. So there's a lot. So there's wood, charcoal, coal. I'm trying to think what else. Dung. Yeah, it's a very interesting. And solid fuel use isn't. So actually, I have relatives in Germany who still cook on wood, because it's like very rural Germany. There's trees. So yeah, there's a lot of solid fuel use all over the world, different countries.
LPG the same as LNG?
Not exactly. So liquefied natural gas is typically like the pipe natural gas to a house. And in this study, so when you do a global study, you have to make so many simplifications because otherwise it's just too complicated. So we kind of made one category of gas, but technically you can see the different categories like LNG, LPG with the data we used. But we had to make a lot of simplifications. Yeah.
one thing is centralized, village.
No, yeah, we pretty much just did like very approximate, like based on population growth and fuel use, largely because, like I said, it's hard to look into all the smaller things on a global scale. And we also, the other thing, we didn't really explore like solar or some of these other things, but that would be something really cool to look through too, I think.
How was the map made?
How was the map made?
Yeah.
I made this map in Python. I use GeoPandas, I think. If you want to make these maps, and I've made much better ones since I made this bigger, you can send me an email. I'd be happy to share if it's useful. Are there any questions from the Zoom chat? Sorry, I forgot to monitor the Zoom chat.
Nothing yet, looks like.
Okay, if there's any question from the Zoom chat, if one of you who are moderating the Zoom, if you can just speak out, that'd be great. Okay, thanks everyone. Okay, are you using here? Are you on? Okay.
We have uploaded. We have uploaded. We have uploaded the slides.
Okay, why don't you? Are you ready to go next? You're on Zoom, right? Okay, 1 second, everyone. Okay, I think this is it, right?
Mhm.
And refresh. Okay. If you want, you can see yourself. There you go.
Hi, good afternoon. I'm Renali. I'm a graduate student from the Civil Construction and Environmental Engineering Department and having a major of construction engineering. So my topic is for presentation is a brief on solar heat for industrial processes. It's a study that I have done on the one publication by the International Renewable Energy Agency. So it's not my research work, it's the study of somebody's research. So introduction about IRENA, it's it's intergovernmental organization, which is International Renewable Energy Agency, which supports all the countries for the sustainable, for the countries who are in a transition phase for the sustainable energy future. And it serves as a principal platform for international cooperation, Center for Excellence, policymaking, technology, and financial education and knowledge on renewable energy. So what is solar heat for industrial processes? The solar heat is gained by the technological things like the flat plate collector or parabolic collectors. And this is used for heating or cooling of the systems required by the different sectors and the operations happening there. So with advanced solar process heat technologies, temperatures up to 400 degrees Celsius can be provided. And it is almost fulfilling almost 50% of the heat demand in the industrial sector. So the applications of these things are like in industries, sectors like food, beverages, paper industry, bricks, blocks, industries, textiles, chemical and plastic. What I could understood that the chemical and textile industries need a lot of heat, and solar panels can generate that much of heat. So I could get one example that they have provided here is as it is back from India, that India is one of the religious countries that they follow more religious practices. But apart from that, here we can see this is a temple, but for this temple, there for food facilities there, the almost 80,000 to 1 lakh people eat daily. So for this processes heat, they need more fuel. So what they did, they have installed this solar panel system, and by using this, the whole food system on daily basis can be done. The operation that happened is like this. They have used the parabolic dish, and like this, the sun rays come on the reflective dish, and receiver receives, and by using this, the heat is generated, and by using that heat, the food is cooked. So, although we are using this solar renewable energy, there are so much barriers to this renewable energy systems, like it needs high investment, and because of lack of finance options as well, there are restrictions to these renewable energy source. Again, the subsidies are provided to fossil fuels in few countries. That's why pricing for fossil fuels is one of the barriers. And still people are not aware about this renewable energy system sources. That's why public awareness is again a need for public awareness. And there are scaling issues that the companies or the small scale industries or the larger scale industries have. There is an issue in scaling of this renewable energy sources. And again, there is a lack of suitable design guidelines. That's why there are limitations right now. The conclusions that they have provided here are the energy input and output, like the cooling and heating processes by using solar energy. Then they have given the process heat demand, like how much energy that can be gained for the unit sector, and how much in degrees Celsius. Again, the sectors, the temperature range and heat intensiveness, like low heat, medium heat, low to medium heat. And the technology variant that they have provided specific thermal heat in kilowatt per square meter. Then the tracking of the parabolic dish. Again, the system size, the number of systems used, then the installed capacity, collector area, total investment, and average investment. So yeah, likewise, they have studied things and presented. The study has been done in 2015. So according to that data, I try to present. Thank you. So if you have any questions, you may ask. Yeah.
What is a parabolic dish?
So it's see, there are collectors of different types. That is a parabolic dish is a dish having parabolic shape with concave lens having, right? Am I right? The parabolic dish is a parabolic collector. This is a parabolic dish. Okay. Yeah. So flat plate collector, and one more type is that something like ETC. You might have known about it. There are two types of collectors: flat plate collector, and one more is there. So. Okay. Okay. Yeah. Okay. Yeah. Converting into the heat.
Okay.
And that heat is used for other what are the purposes? Like, for example, food industry, like pasteurization, drying, cooling. These are the operations that they have in this industry. Likewise, for different industries, they have different operations, and for those industries, heat energy, converted heat energy is used. Yeah. That's a good question, but I don't think I found something in this study, but there is a need to store that energy. Yeah. So yeah, first of all, developing countries where solar demand and sun is in more intensity, it is they should have prioritized these things that they can use more and more solar energy compared to the fossil fuels. Are there any questions? Yeah, thank you.
Everyone, 1 second, we're going to switch laptops. And if you want, you can show the video or.
You have to mute that side.
Oh.
And you want me to share my video?
First, I'm speaking here.
Hello? Can everyone hear me?
Hayden, does this sound good?
Yes, I can hear, can you speak again?
Hi, can you hear me?
Okay, now it's actually a little quiet.
Sorry about this.
Okay.
Do
We
you
can
want
also
to
just,
mute and then open?
I think, let me. Okay, try again.
Hi, can you hear me?
Yes, that's a little bit better.
A little bit. Maybe I need to be louder. Okay.
Oh, wait, no, there we go. Now,
Okay.
now it's,
I just need to be, okay.
Okay. Thanks,
All
everyone.
right.
Sorry about that.
Sorry. Hi, so I'm going to talk about an evaluation of the techniques that I use for citing new wind farms with a case study of Texas. Trying to switch slides. All right, so why is this important? Well, when you look at the power equation for the
producing wind energy, as it is directly related to the speed of wind. So a small increase in the velocity of wind causes a large increase in power production. So it's really important that you optimally site the wind farms. Well, there's various methodology in the literature for siting wind farms. The one that I'm going to be focusing on is the GIS with multi-criteria decision analysis, because that's the most comprehensive. The main factors really for most of the approaches that you look at are mostly wind speed and access to transmission, for the reasons I previously mentioned. So how this works on a high level is you'd look at the most important factors that need to be considered in order to optimally place these farms. For example, wind speed, like I mentioned, access to the transmission lines, distance from transmission lines.
The audio is kind of breaking up a bit. Sorry to interrupt.
Sorry, oops. Sorry about that. How do we?
Now it sounds like more.
Okay, maybe I need to move this way. So sorry. So
you're good.
yes, wind speed, let's say population centers, usually they're a little bit not too close to like the very densely populated areas. The elevation, usually, high elevation is better. If you're like in low elevation areas with like a lot of distractions, then you won't have as much the wind potential. And the current wind sites that are existing now, obviously those are already occupied, so you want to find other areas. And so what you do is you find all these factors, you find the maps for them, the raster file for them. This is using GIS. Then I will basically do a reclassification, and basically based on the weights that are attached to them. Like I said, the wind speed is more important, transmission is more important. Those will have more weights, and then some of the other factors will have less weights. And then I will basically have all these maps overlaid to form what you call a suitability map. That, show the areas.
Let me try. Hello? Okay, that's not good.
With this?
Yes.
Yeah.
Hello, is that better?
Yeah. Yes.
Sorry. All right, maybe let's just go back to the slides.
Okay. You sure?
Yeah, it's fine.
Okay.
Sorry, everyone, I haven't done many hybrid events. Sorry, everyone, like I haven't done almost any hybrid events, so okay, try. And I can start the video. Okay, do you want to try ask if that?
Is that better now?
Yep. I can hear you better.
The volume
Oh,
down.
maybe.
Is that better now? Can you guys hear us?
Yes.
Okay. All right, sorry about that. So, go to the next slide. So I just want to show you what the results look like. The small range of uh, is potential, and on the right use the justice and how we gauge the potential is very strong blue, demonstrated by but then when you look on the other side, on the surface, blue, you know, another sort of layer of the evaluation, and I think that is, more important than just looking at the wind speed. So the suitability map aside, there is the aspect of a lot of literature that's not talking. So what you're looking at is the prices of electricity taken at different times. This is a competitive market, so the price of electricity and you see that the market has been the east side high electricity prices, that's where you find the more demand for this factor. And the prices on the west side are a lot lower. So if I only rely on the previous maybe you see that I'll probably make more money if I do it on the east side because that's where there's high demand. So there's that additional layer that has to be considered when deciding which is the literature does not talk about. So when if I build the wind farm on the east side, maybe I'll not make as much wind energy, but then I'll probably make more money because the LMPs are higher. So then on top of all those, there's another layer which is kind of high level, with a bit difficult to explain very quickly, but in a nutshell, if I'm considering a place to build my new wind farm, maybe I need to look at the wind farms that are available, and I want to make sure that on average, wind speeds are kind of varying with the new site that I want to. This is that and this new wind farms produce a lot of energy high. Maybe new farm doesn't need it's not producing much. That sort of weak correlation between the previous and maybe the new site. So that makes energy, maybe not as much energy, but you probably make more money because there's less production in the surrounding. So the discussion or the conclusion of this is that you really cannot look at one layer of it. I can't only consider stability. Only look at economics is not enough, but it's sort of we need to sort of find a model or a way to sort of more comprehensively all these, link them together. And with all that said, I beg your pardon? No, because this is only looking at what's existing, and really we don't have that much offshore wind energy. I know there's more in the future, but currently so this was mainly, but I believe that some approaches and aspects would be translated to offshore.
There is that 3,000 bars.
That's true. Yeah, well, because the literature that I reviewed they did consider like presence of the state parks, but there was not as much significance. So you basically attach weights based on what you think would, be the relative importance of, one aspect versus another. So you're right, definitely, birds and all that has to be considered, but most of the literature, I think, doesn't put so much emphasis on that. And then the offshore is obviously definitely like, it has a lot of potential in the future, and that, moving forward is going to be the area of expansion. So Texas is the largest wind producer by state in the country. They're like around 30%. And I think, climate change aside, it really ties to potential, unless you're, looking at going offshore. But all considerations, climate change aside, really heavily how much it is, currently. Guess it's
How many like wind turbines are like typically in one farm?
So it varies, depends, is it utility scale? Is it, private? Some contractors or investors will just pay money to like local farmers to just have like a turbine and then sell the energy to them. So it really, varies. And I guess you can see some of, usually when you see the packets together, that's some of them. Picture. Does that answer your question? Thank you. Thank you so much.
I won't apologize. I'm never attended a highway event, so.
Oops, sorry. So I'm presenting on another project I'm working on. So this is a little bit different because I do a lot of, I'm mostly air quality, but I focus also on water, a little bit of the intersection. So this presentation is, do the health benefits of boiling drinking water outweigh the associated impacts of increased household air pollution exposure? So boiling often takes place with solid fuels, and this map shows the premature deaths from unsafe water, sanitation, and hygiene. And globally, 1 billion people lack access to safe drinking water supplies, resulting in 1.7 million deaths annually. And the map on the right shows the global indoor air pollution premature deaths. 2.8 million people cook using solid fuels, resulting in 2.6 million deaths annually. And if you look at the maps, a lot of the countries which have a lot of deaths from unsafe water, sanitation, and hygiene are the same countries that have a lot of deaths from indoor air pollution. And so boiling is the most common household water treatment method with an estimated 1.2 billion users, 70% of all household water treatment users. So the objective was to model the health trade-offs from boiling drinking water with solid fuels. So to see if by boiling drinking water, you're making the water safe, but then you're increasing your exposure to indoor air pollution. So it was purely like a hypothetical study to compare the two health risks. So I'm going to talk about disability adjusted life years, or DALYs. So we wanted to calculate total DALYs for a family in the study. And so for drinking water, we used a quantitative microbial risk assessment for 3 major pathogens: Campylobacter, rotavirus, and Cryptosporidium. And we used different boiling scenarios. And we looked at families' exposure to pathogens from their drinking water. And For indoor air pollution, we used a box model to estimate the 24-hour PM2.5 concentration and corresponding disability adjusted life years, or the DALYs. And we did this for different traditional and improved stoves. And we looked at a family's exposure to PM2.5 from cooking and water boiling. And we ran the model using a Monte Carlo simulation. So pretty much for all our input variables, I looked for data from past field studies and used distributions to try to account for real life variability. And so we found that we compared the benefit of boiling water, DALY's reduction, with the negative impact of boiling water, or DALY's decrease. So on the left, we have the decrease in DALYs for our different water source levels of low risk, medium risk, and high risk. And on the right, we had 2 energy use scenarios. So here we're looking at the difference. So we looked at the scenario where a household already is cooking their food, because you assume they have to cook their food anyway. And if they additionally boil water, like say using the same fire, what is the difference in health risk compared to only cooking versus cooking plus boiling water? Then we looked at a scenario of where they only boiling the water, but maybe they cook their food on a completely clean stove. And so we had our different stove types of the gas, a gasifier stove, which is a type of solid fuel stove that's a little bit cleaner, charcoal, improved wood, and improved traditional. And we had different boiling water scenarios, including ineffective field, low, average, best, and hypothetical lab study. And we found, so we have the benefit of boiling water, and then we have the negative impacts of boiling water. And then in general, and we have increasing PM2.5 for the different stoves. And generally found that the benefits of boiling drinking water outweighed the risks, the negative impact of the increased indoor air pollution. So that's it. I'll take any questions. Yeah. Yeah.
So how would boiling and cooking less of a risk than just boiling?
Yeah, so yeah, I probably didn't explain it well. So pretty much I was looking at the difference. So I was only trying to look at boiling. So obviously if you're cooking and boiling, like total risk is higher. But I try to look at the difference, so just the boiling, because I was assuming, okay, a household. I think what I was thinking about is, I was in the Peace Corps. I used to see all these signs like boil water, and the houses were already cooking on wood. So you figure like if they start boiling, they're probably, they're already exposed. But yeah, I think I could probably explain that better, because definitely it's the combined is bigger, and probably the ultimate goal is to have like a cleaner stove for both cooking and water boiling. Yeah.
The current goal is the goal to switch folks from using carbon-based
Yes and no. So there's a lot of controversy about LPG. So LPG is good because it's a modern fuel, it's clean, it doesn't have a lot of emissions. Because it's a fossil fuel and it's very dependent on fossil fuel production, and for some countries the emissions are still quite high. I wouldn't say it's a perfect solution, but it's a better solution, I think. No.
The goal then to try to minimize the household.
Yeah, so yeah. Yes, that is, yeah, so actually for, in my master's, I actually made this like educational video about like simple ways people could try to reduce indoor air pollution. And we talked a lot about ventilation, because yeah, if you do things like cook outside, that's huge impact, and doesn't cost, or you have to move your stove outside, but it doesn't cost. It's not like trying to get gas stove. So yeah, those are huge. And in my model, I had different ventilation scenarios. I couldn't do all, but I had a few different ones, like high ventilation, or I call it air exchange rate. But yeah, some of those impacts, or like having a working chimney, if you have a chimney, is like huge. So yeah, those are very, very important. Any other questions? All right, thanks. Our final presenter, it's on Zoom. So let me stop sharing. Okay, you can go ahead and share your screen.
Okay. Okay. Hello everyone. My name is Shamik Bhattacharya. I'm an undergraduate senior here studying environmental science. I recently finished an internship at Oak Ridge National Lab, and this is my research. So without further ado, so my work mainly focused on something called cluster analysis. So clustering is what you can actually see in figure 2, but I'll start with the basics. So I haven't seen this stuff in a while, but basically we applied cluster analysis to identify global ecoregions, as you can see in figure 2, and just see what characteristics we saw. We aggregated grid cells from historical land model simulation to see those ecoregions and so on and so forth. So we kind of did like 4 things all in one. So in our first analysis, we used annual means of 19 variables, which you can actually see on figure 4. From a land model simulation to characterize land drivers and hydrological and biochemical responses, averaged over 25-year windows from 1858 to 2008. In the second analysis, we used means and standard deviations. So in the top here, and I know it's kind of small in figure 4, you'll see annual, or just actually annual is spelled out, and then at the end you'll see annual _SD. So that means annual and standard deviation of the same 19 variables, as you can see here. And you just average those out for each 25-year window. And then we used, again, those clusters, as I mentioned, or these K clusters. So these are levels of division. And then we compared those models with the ILAM, which is the International Land Model Benchmarking thing. And then we use Python in a Jupyter notebook to create these maps. This is what we call the multivariable geographic clustering, or the MGC. So there are a couple of things that are in this. So there's a transition from the geographic space, which is the left. An iterative K means cluster, and then back into, these are all the components. So on the first, going to figure 2, sorry, on the top is clustering of 20 groups. So as I mentioned, so K can equal 10, 20, 30, 40, all the way to 800 different clusters. So on the top, K is equal to 20, and on the bottom, K is equal to 100. So that means there should be 20 different colors, 100 different colors. And one of the things that we saw as we increase the K cluster value, the maps actually get more and more detail, showing off the structure of the original model output as the level of divisions are increased, or by the values of K. But what I can also see here is that we can't really determine what each color is, because it blends in with another continent. Here in figure 3, we just evaluated those, so we're just looking at the scores. So again, beyond the cluster of 100, we just see that it's doing pretty well. Going on to figure 4, so these are variables. So one variable might be gross primary productivity, or net biome productivity. And so these colors down here, so when it starts at a dark orange, that's the worst value. And then when it turns into this dark pink, pink purple color, it's a worse. So when you're comparing to, let's say you're taking the whole global model and you compare it to what the model is saying in the map, these are just the color context. So at, let's say, annual at 10, let's say, it's just very worse. And then as you keep going on, but we only selected 19. And just wrapping up here, So we can just see as the level of K divisions keep increasing, the number of ecoregions keep increasing, and the nominal size of the ecoregion decrease. Thus, the regions become more specific and defined. And I think what this my research actually showed is that we need to like work on a lot more about MGC, cluster analysis, and just like the work that climate modelers need to keep doing. And we can basically use ILAM as a test, basically, to if we keep inputting more variables, we can find out where the downsides are. And the last thing I'll just say is a modeler may use all this information to select a sufficient level of division and use the K-realized centroid grid cell as a representative of ecoregions for modeling studies. Thanks again. And if you have any questions, let me know.
Could you hear the question or should I repeat it?
Please repeat it.
Okay, all right, sorry. So the question was, why did you choose K-means cluster? There's many other clustering algorithms, so why that one?
So my mentor, who's Dr. Forrest Hoffman, he actually suggested because the other clusters are kind of advanced and I'm still learning. So I think the K clustering was kind of an easy first step to learn. And I'm actually going back to this internship, so I should probably, probably go to the next clustering, problem, if you will.
Thank you very much for presenting. We appreciate it.
Mhm.
Who was your internship for?
Oak Ridge National Laboratory.
Okay, cool. Thank you. All right, and then so I know we're right at 5, so what we'll probably do is let me make sure I'm unmuted. Oh, I forgot to share my screen. 1 second. Sorry, I forgot to share the screen. Okay, so I think what we'll do, and I don't know, I can, for those of you on Zoom, hopefully the QR code works. Otherwise, I can put the link in the chat. If you want to go ahead and vote, but I think because we're out of time, we'll tally the votes and send an email. So go ahead and take your time voting. And I sent the link to the abstracts. So if you can't remember who presented what, you can refer to that. So cool. So did everyone is the QR code work for everyone on Zoom? Let's see if I can get share the link. It's okay. No, let me know. Okay, just give me a second.